Hello and welcome to this lesson where we're going to be talking about the different types of macronutrient in a little bit more detail, what they're used for by different athletes and their relevance in sport, and also their actual chemical structure and how they're grouped together. Firstly, we're going to start by looking at carbohydrates. If we wanted to classify carbohydrates, we can talk about their structure and how large they are. Monosaccharides and disaccharides are single or double sugars. Then we've got complex carbohydrates, which are the likes of starch, cellulose, and glycogen. This is quite an important distinction, as you'll find out later, because it determines how fast they release the energy that's stored within them. The more complex, the longer it takes to release the energy. Mainly we're going to be talking about glucose in terms of breaking down carbohydrate to form glucose, which can then be further broken down by our energy systems to produce ATP, or the body's currency of energy that we need to use to power muscle contractions. But there are other monosaccharides as well. They'll just enter these energy system chains at slightly different points. Taking glucose as an example then, it is a classic hexose sugar, so it has 6 carbons. So the ratio of atoms is 1 to 2 to 1. That is that they have 2 hydrogens for every carbon and every oxygen. Glucose is an example of a monosaccharide where there is just one single sugar. Other examples include fructose and galactose. Disaccharides happen when monosaccharides group together to form chains of 2. An example of this is sucrose, or what we otherwise know as normal table sugar that you'd put in your coffee. And this is what we get when we combine glucose and fructose together. The process of combining 2 monosaccharides to form a disaccharide involves a chemical reaction called a condensation reaction. We can see in the case of creating sucrose from glucose and fructose, a 1 to 2 glycosidic linkage is formed, and that produces an additional water molecule. Any reaction where water is produced is known as a condensation reaction. If we look at this reaction in the opposite direction, so sucrose being broken down into the individual monosaccharides of glucose and fructose, we can see that we actually require water in order to be able to split the 2 monosaccharides. This is known as a hydrolysis reaction, so water is used up or required. And this is one of the reasons why, although water itself doesn't give us energy or calorific content, it is a macronutrient, because without it we can't break down the carbohydrates that we need to provide us with energy. Now, hydrolysis or hydrolysis is the word used to describe the splitting or the breaking up of water. So in this case, we start with water and it gets split into an OH and an H. Lysis just means the splitting of, and this is an ending that will come up a couple of times in this unit. Just be aware that this is not the same as if sugar goes into a cup of tea and it then dissolves. Another example of a disaccharide is lactose. Lactose is found in milk, and we break it down into its constituent monosaccharides, glucose and galactose. This takes a specific enzyme, lactase, and humans are unusual in this capacity because most mammals stop drinking milk after childhood and so lose the ability to break down lactose. In humans, however, we retain this ability as we retain the production of lactase as an enzyme to perform this function. Although in some members of society they can be lactose intolerant and they can have problems with this process. If we look at an overview of the metabolic pathways, we can see that the monosaccharides fructose, glucose and galactose simply enter those pathways at slightly different points. The end result of that initial breakdown is going to be the same. In addition to mono and disaccharides, we can also talk about polysaccharides, and these are where individual monosaccharides undergo a series of condensation reactions to build up into long chains. Starch, glycogen and cellulose are 3 common polysaccharides that are formed just from glucose molecules. And we can see the difference really is in how they're structured. The type of bonds between each glucose molecule differ, and so therefore the structure of each polysaccharide is slightly different. Starch would normally be found in high carbohydrate foods such as potatoes and pasta. Glycogen is our storage form of carbohydrate. When we consume a meal and we want to be able to store that carbohydrate for later use, we'll turn it into glycogen and then it gets stored in the skeletal muscle and the liver. Next then, let's go on to talk about fats. You need to be aware that there's a number of different names in the syllabus that refer to fats. They can be called triglycerides, triacylglycerols, or just fats. Within the scope of this syllabus, these are interchangeable words. Just be aware any of the different terminology could be used in an exam question. Triglycerides or triacylglycerols are mainly a type of storage lipid which are contained within the adipose tissue of the human body. They constitute a very concentrated supply of energy within the body. As the name triglyceride suggests, there is a glycerol backbone and then 3 fatty acid chains are attached to that. The different type of fatty acid chain will determine what type of fat it is. We can see here how the glycerol head attaches to the 3 fatty acid chains. In attaching, we again see a condensation reaction where 3 H2O are produced in the attachment of the 3 fatty acid chains. When fats are broken down to produce energy, we'll see the opposite and we'll see a hydrolysis reaction in order to remove these fatty acid chains from the glycerol head. A fatty acid chain is a carboxylic acid chain that is either saturated or unsaturated. As we can see here, we've got a backbone of carbon atoms down the middle of the fatty acid chain, and attached to that we have hydrogen atoms branched off. We can see that in the saturated fat, all of the available links between the carbons are taken up by either linking to the next carbon or to a hydrogen. In the case of an unsaturated chain of fatty acids, we can see that there are places where there are double bonds between the carbons, therefore meaning that they are not carrying as many hydrogens as they possibly could. If there's one double bond between the carbons, then this is known as monounsaturated. If there's 2 or more, then it's known as a polyunsaturated fatty acid chain. Saturated fatty acids, because of their uniformity, lie straight, and so therefore they can be packed in very densely, so saturated fats contain a very large store of energy. Unsaturated fatty acids, on the other hand, where there's a double link between the carbons in the chain, there's also going to be a slight change in angle of that fatty acid chain. This means that when they sit together, they don't sit together quite as closely, meaning that it's not quite such a concentrated store of energy. Foods that contain large quantities of saturated fats are, for example, butter, dairy products, and also meats. In addition to that, we can see some tropical oils like coconut oil and palm oil. Diets that contain lots of saturated fats are likely to result in medical issues such as atherosclerosis and coronary heart disease. Unsaturated fats, on the other hand, will contain a slightly lower density of energy than saturated fats. This means that they're slightly healthier, but their intake will still need to be limited by most people. Unsaturated fatty acids can be found in foods like avocado, nuts, and olive oil. Finally, we'll talk about the role of protein. Proteins are highly complex and do a number of different jobs within the body. For example, they make up enzymes, hemoglobin, which contributes to the oxygen carrying capacity of the blood, and muscle tissue. Even your fingernails and hair are a type of protein. Proteins are made up of strings of amino acids. There are 20 amino acids in existence, and the exact order of these amino acids will determine how the protein forms and what job it does. We can see if we look at the structure of an amino acid that they all have the same starting structure. The difference between the amino acids will be determined by the presence of the R group. If we look in a bit more detail then, we can see that the main structure is composed out of carbon, oxygen, hydrogen and nitrogen. The R group, or the side chain, this is what's different from one amino acid to the other. For an example, here is methionine, which is one of the amino acids. We can see the standard structure at the top of the amino acid, and we can see the R group strung out underneath. Amino acids then are the essential building blocks for proteins, and they're vital in a number of chemical processes that are really important in sports. For example, we've already spoken about neurotransmitters. We've already mentioned as well enzymes, and in the cardiovascular system we talked about hemoglobin, which is a protein. They're also involved in the creation of hormones which will regulate the body's systems. As I previously mentioned, there are 20 known amino acids, 9 of which are essential. These 20 amino acids can be combined in different ways to produce more than 40,000 different proteins. 9 of the amino acids are what we call essential. This means that we have to get them from our diet. We can't make them in large enough quantities in our own body. Good sources of these amino acids are things like meat, fish, eggs and dairy products.